All right, so we're going to talk a little bit about summations for a bit. And the idea behind summations is it's just simply taking a series and adding it together. Remembering that a series is the sum of a sequence, and the sequence is a collection of numbers, objects, or whatever that all fit together. In this particular context, we're going to deal with numbers exclusively for those sets, meaning that we might have a set that's defined by, let's say f of x is equal to, I don't know, 9x squared plus 2, okay? And let's just say that my x values here go from 1 to, I don't know, 3, okay? Well, in that case, if we're talking about discrete values, meaning countable values, the only values we would have would be 1, 2, and 3. So we'd be doing f of 1 plus f of 2 plus f of 3. And this would be just simply finding that sum, where f of 1, you just stick 1 in. 1 squared is 1 times 9 is 9 plus 2 is 11. 2 squared is 4 times 9 is 36 plus 2 is 38. 3 squared is 9. 9 times 9 is 81 plus 2 is 83, which gives us a grand total of 11 plus 38, which is 49. 49 and 39 give us 131. No, I'm sorry, not 31, 32. Sorry, 32. Okay, 132, if I did my math correct. So this would be the sum. So we're talking about the summation from k equal 1 to 3 of f of x. That is what we did right there, and that sum is 132, assuming I can add correctly. Some of you may send me an email saying, hey, you added this wrong. That's fine, but I hope you get the idea there. All right, now, continuing this on, let's just say that we're talking about doing the summation from k equal 1 to some other quantity of, I don't know, let's say 5 of 3x minus 7. Well, that just simply means plug in 1, plug in 2, plug in 3, plug in 4, plug in 5. And then you just simplify that, right? So you just go through that entire list and you find out what that sum is of all those pieces. A lot of adding and subtraction as you go through there. And of course, in this particular instance, there's actually some pretty easy ways to do this calculation. You could do each one individually, but if you notice, each one has a 7, each one has a 3 in there. So if you look at this, what you're dealing with is 1, 2, 3, 4, 5, negative 7. So it's 5 times negative 7, right? Plus 3, each one has a 3. So we're really looking at 3 times 1 plus 2 plus 3, which is 6, plus 4, which is 10, plus 5, which is 15. So you got negative 35 plus 45. Again, if I'm doing my math right, and 45 plus negative 35 is 10. So my sum there would be 10 for that summation. Okay, so that just simply means all we're talking about when we talk about summations is just simply take all these pieces, plug in 1, plug in 2, plug in 3, and on down the line and add them all together. Now, what do we do when we have something that is maybe a little bit larger or too big for us to actually add all those individual pieces together? What do we do in those instances? Well, we have these processes, these other processes that we can use. So what we have, and we can go through and prove all this stuff to you, but I'm just going to simply write down the formulas right now for you. If we want to do the summation from k equal 1 to n of some constant c, that's what c is here, is just a constant. That constant, or that sum of all those pieces, would just be n times c, or just nc, whatever it is. So example being, if you're doing the summation from k equal 1 to 50 of, I don't know, 7, just the constant 7. So that's 7 times 50, which in this case would be 350. And that's the sum, okay? summation from k equal 1 to n of k, meaning just some linear expression of some sort. And you keep in mind that there could be a variable here, not a variable, pardon me, a constant here or a coefficient right here, which is some value of a. That doesn't really affect it a whole lot because we can rewrite this as a times the summation of k equal 1 to n of k. Okay, so example being, if we wanted, oh, I forgot to write down the formula for you, sorry. That'd be n times n plus 1 over 2, okay? Now, let's just say we want to do the summation from k equal 1 to 10, which would be a lot of pieces to plug in. You saw how long it took just to do that for 5. It's not terribly difficult, especially when you have some little tricks you can use here and there to kind of do the processes. But let's just say we're doing 3 times k, or 3x would be another example of this. So we're talking, we have the expression of 3x, or 3x plus 7, right? Or 3x minus 7. We could do that as well. We could just simply break them up into their individual pieces. So maybe the original expression here was 3x minus 7. We did it for 7, and so that means we need to subtract off 350 when we're done, assuming these would go, we're going to the same place, but one's going to 10, one's going to 50, so we couldn't do that. All right, just kind of explaining how another way we could have done that previous problem here, and I'm actually going to go back and rework that here in just a second. So we got 3k, so what that means is that we can move the 3 out in front of the summation and just do the summation separate from the 3, so we do 3 times n, which is 10, times n plus 1, which would be 11, over 2, right? So that gives us 3 times, we can cancel the 2 and the 10 and get 5, so that'd be 55, and 3 times 55 would be, 165? Okay, so there's that summation. Like on the previous example, I was doing the summation from k equal 1 to 5, of 3x minus 7, right? And that gives us, if we're going to split this up, we're splitting it up into 2 pieces, into the linear piece and to the constant piece, and we're just going to put a minus sign between them. So we're doing the summation from k equal 1 to 5 of 3x, which we would treat times 3 times that sum, minus the summation from k equal 1 to 5 of 7. And if you watch what we're doing here, we now have 3 times 5 times 6 over 2 minus 5 times 7. That should look a bit familiar if you go back and you've written that down. And then you end up with the 6 canceling with the 2, and you have 3, so you have 3 times 15 minus 35. That's 45 minus 35, which is 10, which is the same thing we got last time. So yes, this is another way to attack and deal with that same set type of problems. Okay, I'm just working through a few examples here to try to help you and get a better understanding. There are 2 other formulas that you should probably be very familiar with. They are the ones for square and the one for cubes. I'll kind of leave that to you. I don't always write those down. They're very easy to find. You can do a Google search really fast and find them extremely easy. They should also be in your text. And as we come across them and need them, I will write them out for individual problems. I guess the summation for square is one that you probably would use quite a bit. So you're going from k equal 1 to n of k squared. And that one is going to be n times n plus 1 times 2n plus 1 all over 6. All right, now that seems weird, but that's just the way it works. All right, more to come. Exciting about, I hope you're getting excited about calculus. I know I stay excited about calculus because things are always changing with calculus. Little math pun there for you. Take care. Bye-bye.